And so yeah, recording is now in progress. I'm going to share my screen. Right. I believe my screen is visible, the recording is on, and we are all set to start our class. So welcome to class number 14 of our course on network fundamentals for cloud. Um, we've extensively covered until last class the topic of data center networks, and we've also looked at multi-site data center networks. So today, as I said last time, we will move up the layer, up the ladder, one more layer, and we'll look at the topic of networking from the perspective of the overlay networks, the virtual networks. Right? So that is what we will talk about today. So when you look at the overlay networks or the virtual networks, from their perspective, the networking involves connecting virtual machines, the other virtual network functions like the routers, the switch, V routers, V switches, firewalls, gateways. Those are all the virtual network functions that exist in the overlay network. And a lot of times, especially true lately, is the approach to use containers as a method of deploying applications. So many times the VMs are either containing containerized or running containerized applications, or in rare cases, it's also possible to run these containerized applications directly on physical servers. So either way, containers need to connect to other VMs, to other containers, or as part of the overlay network. So all these requirements from a networking standpoint exist in the virtual network that we've created on top of the data center network. And how that networking works is what we are going to look at today. Part of today's discussion is also going to focus on the performance from a networking standpoint, the network performance that we observe and the degradation that results in the network performance when we look at throughput or latency and the other elements of delay, elements of processing that get introduced when we look at networking in the layer that sits above the virtualization layer. So that is another thing that we are going to discuss today. What is the impact to network performance when we look at these virtual networks? And after and looking at these network performance impacts, we'll also try to talk about ways that can be used to improve the network performance. What can be done? What are methods that exist that can be utilized to improve the network performance at the overlay network layer? So if we just look at how the deployment of applications has evolved over a period of time, especially from the perspective of data centers, right? So that's where our focus is. Traditional data centers were, when the virtualization concept wasn't even so much there, the traditional data centers, which largely were private enterprise data centers existing within large enterprises, they followed a traditional model of deployment, which meant that these data centers hosted a lot of physical server infrastructure. Every physical server was running its operating system, its own operating system often, and applications were deployed directly on these physical server machines to cater to the client traffic. So this is what the traditional data center deployment model was. As public cloud infrastructure became possible and due to the introduction of virtualization and the ability of the hypervisor or the virtualization layer to provide isolated execution environment to multiple tenants over the same physical infrastructure, we moved to a deployment model which we call as the virtualized deployment model, where I use the hypervisor in the form of a virtualization layer that sits on top of a larger physical server machine. And it provides me multiple isolated execution environments, each of which is called a virtual machine. every virtual machine can have its own operating system, which we call as the guest operating system. And it has its own tech stack for running the required applications. So what is important is to realize that this distinction between two virtual machines, these we are saying that this is an isolated environment. I mean, they don't interact directly amongst each other. It's like running a VM on its own physical server. Right? So this is what mostly we follow in a cloud-based data center environment. But more and more containerized deployments are becoming popular because containerized applications are packaged to be standalone, carrying all the required third-party libraries, runtime environment that is needed to run that application in the form of a single package. I can just move that package one machine to the other and it seamlessly continues to work with all dependencies taken care of already in the containerized package itself. So the whole idea of containerized applications has grown and a lot of it's very popular. And last time I had asked you if you've already covered the broad topic of containers in cloud computing course and you said yes. So I'm assuming this is something which has been covered. So a pure container deployment basically requires you to run a container runtime instead of a hypervisor. So the container runtime is creating a different kind of a virtualized environment. The isolated environments for each container to run are provided by this container runtime as against the hypervisor. The benefit of a container is also that it doesn't require its own operating system. The containerized applications actually use the services of the host operating system underneath. So that's what we are today calling as the container deployment. Now, hybrid deployment models in between these three architectures are also possible. So if I look at a modern data center environment, I can have all these options. I can have a pure containerized deployment model. As you see over here, this is container one, this is container two, this is container three. I'm using Dockers as the containerized container runtime. And I can run these containers C1, C2, C3 on a physical server P1. Right? On another physical server P2, instead of having the Docker runtime engine running, I can have a hypervisor, which could be bare metal hypervisor or could be running on top of a host operating system, depending upon whether it's type 1 or type 2 hypervisor. But on top of it, each of these are VMs. Right? So I can have a VM1, a VM2, a VM3 running on physical server P2. Now, a VM can be standalone VM running one application or a set of applications as we see in VM3. But what is also possible is to take a VM like VM1, which has its own guest operating system, and assuming that this is Linux or a variant of that, we can run the Docker engine on top of Linux within a virtual machine as well, and then have other containerized applications C4 and C5 running within a virtual machine as well. Right? So on the previous slide, what we saw was more pure play deployment models, the traditional one, the virtualized one, the containerized one. But here we are seeing more of a hybrid where I have the virtualized deployment architecture, but within a virtual machine, I can further using a containerized deployment model. So if you look at your data center or from the perspective of your overlay network, your overlay network could be this. Right? This could be your overlay virtual network that has been created where you have 5 containerized applications C1 to C5 running along with 2 virtualized applications App6 and App7. And all of them have requirements to connect to each other or talk to each other. They're all networked applications. So what we need is the virtual network or the overlay network to be able to support this kind of communication between VMs, between containers, and that is where today's lecture or topic comes in. So I'm skipping this slide which talks about what are containers because I believe you already have covered this in the cloud computing course. I'll directly move towards the networking topics in this. So when we looked at the VPC as it is depicted inside of AWS, okay, we saw that there are a lot of these instances of virtual machines, which we are calling as the EC2 instances. Of course, there are other types of virtual machines as well, but EC2 is the most commonly used one. So these are EC2 instances. And when we saw these arrows, these were nothing but traffic exchanges that was happening between VMs. One EC2 instance communicating with another EC2 instance to create the web tier, app tier communication, the app tier, database tier communication. So this is VM to VM communication. But we also saw that there are network appliances like the router, virtual router, the internet gateway. Right? There were other things like the site-to-site VPN. So there are a lot of these virtual network functions which are enabling the interconnectivity of the VMs across subnets within the VPC. Right? So there are network appliances like the NAT gateway, internet gateway, router, load balancer. All of them can be called as virtual network functions, and they need to be part of this overlay network. They need to be handling traffic that is flowing within the VPC. And lastly, we said the third requirement is traffic exchange between containerized applications, where the containerized applications could be part of a VM or directly running on top of a physical server. Okay? So all these three are the types of traffic that we see or observe in an overlay network. And we'll today talk about this part of our networking topic. So let's start with the networking in the virtualized deployment architecture, leaving aside containers for a bit, and talk about in an overlay network, how do VMs or virtual network functions enable overlay networking. So one of the key virtual network functions that exists in the overlay network and is part of every hypervisor or part of the virtualization layer is the virtual switch, the V switch. Okay? So the virtual switch, as the name suggests, it's virtual in the sense that it doesn't have an associated hardware of its own. It's a software-based switch. Okay? It resides inside the hypervisor kernel. It is the network appliance that is enabling local network connectivity between virtual machines. And of course, we'll extend it in the latter part of today's class and say also containers going forward as containerized deployment becomes possible. And just like a physical switch, a virtual switch has all the layer 2 functions that are required for it to be called as a switch. Right? So it has the flood and learn functionality that a physical switch has, which we are calling as MAC learning over here. It has link aggregation features where we saw that more than one physical links can be aggregated to see them as one link of higher bandwidth. That's link aggregation. It has its own associated protocol. So all these features that a physical switch has, quality of service, VLAN, all of them, fault management, flood and learn, all features that a physical switch has, a virtual switch implements all of them. The only difference is that all these functions are implemented in a software-based implementation, and hence we are calling it a virtual switch. The most common virtual switch that we use today is an open source implementation of the vSwitch, and therefore it's called Open vSwitch or OVS. Right? So OVS is something that you'll find very commonly being used across data centers and in the virtualized environment because it's open source. I mean, anybody can use it. It's not a licensed piece of software, and because of being open source, it's evolved and the features into the OVS have been contributed from the community. So it's grown and evolved very, very quickly and very fast. In fact, there are variants of the OVS which help improve the performance of OVS, which we will talk about later when we come today to the discussion about network performance. I'll talk about variants of OVS also. But essentially, it's a virtual switch, right? Implemented in software. It uses virtual network bridges, layer 2 flow rules in order to switch or forward packets at the layer 2 of the protocol stack. Okay? So it behaves like a physical switch, only virtualized. Like a traditional switch, it maintains information about connected devices. So it has its own forwarding table. It knows which MAC address is reachable via which virtual port. Okay? And so it supports the other overlay networking protocols, right? Remember when we talked about VXLAN, we said a key entity in the VXLAN is the VTEP, which acts as the network virtualization edge. Right? It's the VTEP. So OVS can act as a VTEP. It can be that network virtualization edge, which enables VXLAN tunneling. Right? So OVS even supports these overlay networking protocols like VXLAN, and we had noted then that GRE, generic routing encapsulation, is another variant or alternative to VXLAN. It supports even GRE. So OVS is completely prepared as a virtual switch to operate in a multi-tenant cloud environment. Right? That's what it is. Now, if you look at the helicopter view of what is the OVS architecture, it's like a Linux bridge, as I said, with its own forwarding flow rules. So, yeah, one thing I forgot to mention is it's also SDN compliant. So these OVS is actually supporting the open flow protocol. Right? So when I said it's completely having all features required for a supporting overlay networking in a data center environment, it includes also SDN support. It's open flow compliant. So this is how it'll look like. I mean, you have a physical server in a rack. So let's say this is the physical server. That physical server has a physical network interface card. So we will use the term PNIC, P standing for physical, just to differentiate it from a VNIC, a virtual network interface card. Network interface card, everybody understands. Right? It's the uh, hardware card. I mean, traditionally, it's been a hardware card that we have in our laptops, in our computing machines, that implement the layer 2 protocol and provides the external port connectivity outside of my machine. So you have this physical network interface card, which is providing the external world connectivity in a data center network. This is what connects to the leaf switch or the top of rack switch, which then connects you to the rest of the data center network, right? So we've just picked up one server, one physical server with its network interface card that we are calling S0. Right? Now, the physical network interface card has connectivity to the OVS bridge, the Open Virtual Switch bridge. And OVS, as we said earlier, maintains its own set of flow rules. So for any traffic that is meant outside of the virtual machines, the traffic goes to the normal IP stack in your host operating system. This is part of your host OS via the OVS bridge. But traffic which is meant towards the VMs, right? So remember we said this is part of your hypervisor. It can be sent using virtual ports, V ports. So these are nothing but, you can think of them as, I mean, this is some form of IPC, inter-process communication, because in reality, this OVS is also a piece of software and your VMs are also running in software. So essentially, this is a form of inter-process communication. But we call it a virtual port, right? So that VM see it like a physical port with which they are connected. And this internal F0 that you're seeing, these are actually the virtual NIC cards that a VM has, VNICs. And the VMs connect using this IPC mechanism to the OVS bridge. So the OVS bridge, based on its internal flow rules, will forward the traffic towards the right virtual machine. And these flow rules are either configured, as I said earlier, via OpenFlow from an SDN controller, or they can even be self-learned using the flood and learn functionality. Or in the VXLAN, it could be multicast flood and learn, right? Or MPBGP. All those methods of learning are implemented as part of the OVS. So this is how the connectivity exists within the physical server. Yeah, this I've said, it's licensed under the open source Apache 2 license, supports multiple Linux-based virtualization technologies like Zen Server, KVM, VirtualBox. OVS can be run on all of them. Now, so we've said it supports all, it's a full featured switch. It supports high performance forwarding. Now, high performance is relative. Of course, it's not as high performance as a physical switch can be because it's implemented in software. But the architecture of the OVS is built in such a fashion to mimic a physical switch. So when we looked at network appliances, we said every network appliance has a data plane, which is also called the fast path, which has to operate at much higher performance. But it also has a control plane, which is called the slow path, which doesn't have the same requirement when it comes to performance needs. And then it has a management plane. The OVS has a similar kind of an architecture. The fast path of the OVS, which has to handle the data traffic, is yes implemented in software, but implemented in the form of Linux kernel module. So it runs as a kernel module .ko as part of a Linux machine. And as we know, kernel modules have a higher priority and can attain better performance as compared to a user mode module. Right? So I'm assuming in you have some background into operating systems, and you know that in a Linux environment you have a kernel mode and you have a user mode. All our regular applications run in the user mode, but all system functions run in the kernel mode. So OVS fastpath, which is handling the data plane, runs as a kernel module, which gives it the higher performance. Whereas all the control plane functions, they run as in the user mode, right? As if they were any other application. So all the other control plane functions include your 802.1q VLAN functionality with the VLAN trunk and access port. It supports the SDN OpenFlow protocol. When we come to the topic of observability, we will see there are protocols like SFlow, NetFlow, which are used in network observability. OVS supports them as well for mirroring and for increased observability or network visibility. It supports all QoS configurations, traffic policing. It's a typically layer 2 networks have token ring or leaky bucket kind of algorithms that they use for traffic policing, all part of OVS. It supports tunneling protocols like GRE, VXLAN, and some others. It supports the 802.1 AG standard, IEEE 802.1 AG, which is actually focused on connectivity fault management. So having being a VNF itself, which means it's supporting the NFV architecture and with SDN support, Open vSwitch is the heart of our modern data center architecture. It's an SDN driven virtual switch that can plug into most virtualized environments. I mean, even when you use an OpenStack, which is itself an open source um, NFV architecture, right? An implementation of the NFV architecture, but an open source implementation. OVS is part of the OpenStack uh, uh, implementation as well. So it's heart of our modern data center. So when we look at the architecture of OVS, just to understand where is it that the performance challenge comes in and how it is implemented. Okay, let me skip the uh, text. Let me just jump to the diagram directly. So as I said, it's a Linux machine. So you have the kernel mode and you have the user mode. The fast path, which is handling the data traffic or the data plane of the OVS, is running as a .ko, as a kernel module. It's called the Open vSwitch.ko kernel module. That's the fast path. Whereas the user mode has all the other functions required to implement the control plane and the management interface to the SDN controller as well. So you will find that there is a database which holds all the configuration information, flow rules, everything. So that is called the OVS database or the OVS DB in short. So it's called server because it's in the client server architecture. It is acting as a server. It will receive connection from external clients, client applications uh, to receive configuration information and update it in its database. So it's a database server. It's the OVS database server. Whereas the OVS vSwitch D is actually a daemon process, right, that is running to implement the core control plane function of the OVS. Okay, so OVS vSwitch D is a daemon process which implements and controls the switch on the local machine. So it's like the control plane of the OVS. And it's largely sending the control plane commands to the kernel module, which acts as the data plane. So we saw earlier the architecture where the data plane receives the flow rules from the from the control plane, and that's how the data plane operates. So OVS vSwitch D is the control plane in this case. The kernel module is the data plane, and the DB server is the lightweight database server that where all the configuration information is stored. The flow rules, the VLAN information, all of it is stored inside. The rest of them are all CLI based tools that are used for configuration. So there's a tool called wherever you see CTL, it's control. Right? So there's an OVS DPCTL. DP means a data plane. So this utility, as you can see from the name itself, it's an OVS data plane control tool. A tool for configuring directly the data plane switch kernel module and controlling the forwarding rules. VSCTL configures the VS switch D. Right? It's a utility for querying, updating configurations of the OVS switch D. Then there are other supporting tools. This is a key one. The OF here stands for OpenFlow. So this is an OpenFlow control tool. It's a utility that is used for querying and controlling OpenFlow compliant switches. Okay? So this is the interface towards the SDN controller. The SDN controller will send its OpenFlow commands. OVS, OF, CTL will receive it and then use the internal other applications to configure it in the DB server. And if any changes are to be done in the OVS vSwitch D, then this is what does it. There is a test controller, which is a simple OpenFlow controller that is mimics an SDN controller, but used largely for testing of the OVS. And then an OVS DB monitor as a supporting tool, which is a GUI-based utility that helps you see the data that is stored in the OVS DB server. So there's the key OVS, and then there are supporting tools that come alongside it. Right? So VSCTL manages the OVS DB server, the all configuration. AppCTL sends commands to the OVS vSwitch D. DPCTL controls the Linux kernel module. And OFCTL works with the SDN controller supporting the OpenFlow protocols. And then there is the monitor and the test controller. They are the other supporting tools that OVS has. Now, like a physical switch, the traffic forwarding in the OVS is happening in the kernel module itself. Okay, so we saw OVS has a direct interface to the PNIC. This is the physical NIC of the physical server. This is the physical server. And there is this SDN controller that exists somewhere in the data center. So the SDN controller is sending OpenFlow rules, flow rules to the OVS vSwitch D in the control plane, via all those utilities that we talked of. The VMs, and later we will see even the containerized applications, they always run in the user mode of the Linux operating system. Only Linux system processes and the OVS database path, they run in the kernel mode of the Linux operating system. So any traffic that enters the PNIC from the physical underlay data center network, it reaches the OVS data path and it is forwarded by the OVS data path, as we said, towards the right VM. Right? So in a sense, we are seeing that the packets are directly flowing through the OVS data path. And that's why the data plane is, we are calling it a high performance data plane, because it doesn't leave the kernel mode. It's completely handled in the Linux kernel mode. But when the data path doesn't have the flow rule for a particular packet or a flow, because it's the first packet that is coming in and no flow rule is configured in the data path. This is the same challenge that physical switches have. a packet comes in from the physical interface and no forwarding rule is found in the data forwarding table. So what does the data plane do? We had said earlier also the data plane can do nothing but to discard that packet because it doesn't have a rule to forward that packet, but it just doesn't silently discard it. It forwards it to the control plane. It says, this is a packet that I received. I had no forwarding rule configured. Can you get me a forwarding rule? And that's where the control plane kicks in. So that's what happens with the OVS as well. When the first packet comes in and there is no flow rule in the data path, that packet goes to the control plane. The control plane will then figure out how to configure a forwarding rule for it and put it into the data path forwarding table, after which the subsequent packets can be directly forwarded through the kernel itself. So this is a simplistic view of how OVS handles traffic. But to look at the performance challenges with vSwitch, we will have to go a step deeper than this diagram. This is a very helicopter view. But we will have to go a little deeper into this in order to see, okay, yes, the traffic comes into the OVS data path, but if it belongs to a VM, which sits in the same machine, it'll actually go this way. Right? So there is a path which is created between that takes the traffic from the kernel space to the user space. Now you would say, yes, that happens even in a physical server. When I have a physical Linux server, what is the stack? There is the physical layer 1, there is the layer 2, there is the layer 3. The layer 3 is part of the Linux kernel. That's the network stack. And then layer 4 and onward, layer 4 is also part of the Linux kernel stack. But layer 5, which is the application layer, applications are all running in the user mode. So when in a physical Linux server, a packet arrives, a packet arrives from the physical network interface card, it gets processed in the Linux kernel up till some time. But at some point in time, from the TCP socket interface, it goes to the application where the application has opened this socket interface, and this transitions the data from kernel mode to user mode. And that happens in a physical server. And this transition, people familiar with operating system concepts will know that results in a data copy. The memory regions. So everybody understands what a random access memory is or a RAM is, what a memory in a system is. The memory is partitioned between two modes, the privileged memory, which is accessible only by the kernel mode applications, and the user space memory, which can be accessed by the user applications, right? The whole RAM or the memory is partitioned by the operating system into two parts. Now, because when the packet arrives from the external interface, it's held in a piece of memory that can be accessed by the privileged kernel mode applications, the kernel modules. The data is over here. But when I have to eventually send it to the application, which can only access user mode memory space, there has to be a data copy that happens. The data, the packet is copied from kernel memory to user mode memory region. Right? So that happens in any operating system. Right? From protected memory to user space memory, the data packet is copying. But that's one data copy that happens in a physical machine. When we introduce a virtualization environment, we create a multi-data copy scenario. Okay, and why is that is what we will, when I said we'll have to dig a little deeper, we'll go a little deeper and see why in a virtualized environment, the data is copied so many times. So this is what I've said. In a non-virtualized environment, the data traffic is received by the physical NIC card. It is sent to the application running in the user space via the TCP/IP protocol stack that runs in the kernel space. So there is one data copy involved from the kernel space to the user space. But when we look at a virtualized environment, right, you will see that there are PNICs, but then there are also virtual NICs, which we saw in the earlier architecture. The OVS connects to a VNIC. Right? There is the OVS itself, which is part of the hypervisor. So the data traversal happens not just from the PNIC to the TCP/IP stack in the host operating system to the application, but it takes a longer path via multiple components that come in between. Okay, so that path is what we need to understand. Okay? So essentially, in summary, it is the PNIC sends the data to the hypervisor, where the virtual switch is resident. The virtual switch is essentially getting the traffic from the PNIC. The virtual switch has its own flow rules. Based on the flow rules, it forwards the traffic on a particular VNIC. The VNIC is what is connecting it to the virtual machine. When the traffic goes to the virtual machine, what is the virtual machine running? It's running its own guest operating system. And inside that guest operating system is the TCP/IP protocol stack of the guest OS. Assuming that the guest OS itself is a Linux-like operating system, it will have its own kernel mode where the TCP/IP protocol stack is running, and it will have its own user mode where the actual application within the VM is running. Okay, so this creates this a virtualization overhead because of this additional packet processing that is happening, and in between many data copies that are happening, which actually have the effect of reduce the overall throughput. So this is what is building up the bottleneck or the latency as well as the delay in the traffic handling. Okay, so again, I am assuming here that you have fair familiarity in operating systems to at least understand that the most time consuming operation in any computing system is the memory copies. Of course, it is less expensive as getting some data from hard disk to memory. That's even more slower and time consuming. But even within, when you do a mem copy, which means a copying from one memory region to another memory region, that takes many CPU cycles. Okay? So if you've done a course where you've covered how instructions are processed in a computing machine, we know that instructions have operations like loads. There are load store operations. There are operations which do some kind of add, multiply, subtract kind of mathematical, or we call them arithmetic logical operations. So ALU operations work faster because they're just doing some mathematical logical operation. But load store instructions take many CPU cycles because they have to do a memory copy. Right? So memory copies are expensive. They take a lot of CPU cycles. Right? And that is where the performance bottleneck comes in. So if I dig a little deeper into the data path, we've said the data path, the physical network interface card, when it gets a packet, how many people have worked on network interface cards or close to the network interface cards in the class? Do you know this concept of ring buffers that typically exists in a network interface card, which creates an interface between the network interface card and the main memory of the CPU? I'm basically talking about kind of a driver interface. Every NIC card has a NIC driver. Right? The driver is implemented using an IPC method that based on ring buffers. Yeah, Ravi has worked on it. So essentially, what does the network interface card do? It is getting a packet from the data center network, from the physical underlay network. It receives a packet. Now it receives the data, it places it into one buffer in the ring buffer. Ring is nothing but it's a cyclic, think of it like a cyclic queue. The queue has buffers, memory buffers, where I just store the data that's coming in. So a packet comes from the physical NIC interface card. I store it into a buffer in the ring queue, in an RX buffer in the ring queue. There, the DMA kicks in, the direct memory access kicks in. It copies that from the ring buffer into the kernel space memory, the main memory, the RAM of my computer machine. So here is the first data copy. This happens in every machine, even without a virtualized environment. This will happen. The PNIC, when it has to put the memory in the kernel memory, it goes via the ring buffer. The way we've optimized this is by introducing DMA. It doesn't take CPU cycles. Right? The CPU is not involved in this copying from ring buffer to main memory. We use direct memory access, a separate controller, a DMA device to do this memory copying, and therefore we free up the CPU from these operations. So the physical network interface card forwards the packet to the main memory via the DMA. The packet comes with a packet descriptor, which includes the location of the memory and the packet size. So basically what we're saying is, with one DMA memory copy, the packet has reached the main memory. After it has reached the main memory, the physical NIC will send an interrupt to the PNIC driver, the physical network interface grid driver. Upon receiving this interrupt request, the CPU will come into picture. Now we will consume CPU cycles. Until now, it was all done via the DMA controller. So now the CPU has been interrupted. It's told that there's a network packet that has come into the main memory. It needs to be processed. Right? So the CPU, upon receiving this interrupt, will trigger the PNIC driver. The driver will come up to service this interrupt request. The PNIC driver will receive the packet and see that it's a network packet, so it needs to be given to the network stack, the TCP/IP protocol stack. So the network stack is also part of the kernel space. It's running in the kernel module. I said it's part of the operating system, so it runs in the kernel space. So there is no additional memory copy here. The same memory region is accessible also to the network stack. It's just that the PNIC driver triggers the network stack to handle. It gives it the pointer to the memory location saying, this is the pointer to the memory location where the packet is, handle it. The network stack will then take that packet, and we all know the interface between the TCP/IP protocol stack to the applications that sit on top is what? This is called the socket interface. If you've done any form of network programming, TCP/IP network programming in your college days, you would remember this, you would know the socket interface. Socket is the IPC mechanism between the TCP/IP protocol stack and the application. So the TCP/IP protocol stack, the network stack will take this packet, put it into a socket, okay? A socket receive buffer. From the socket receive buffer, the OVS picks it up. Okay. The OVS will now process this packet and determine that this packet is meant. This is the OVS data plane. Right? So it's part of the kernel space itself. It determines that this packet belongs to a VM within this physical machine only. So what does it do? It has to forward it to the virtual NIC. Right? So the packet is processed by the OVS and sent to the virtual machine. This is where the first data copy happens because it's sent from the kernel space to the user space. Again, as I said, happens in every machine. As soon as the packet goes from the kernel space network stack to the application in the kernel user space, the mem copy will happen because the packet which was in protected memory will get copied to a different memory, and that's happening via the socket interface. The socket memory is actually the memory which is accessible via the user space applications. So the packet is processed by the OVS, it is sent to the VM, and here is where the kernel to user space data copying happens, and this consumes extensive amount of CPU cycles. But we can't avoid it. It has to be there. It exists in every physical server. Now, once the VNIC receives this packet, the same processing as what happened in a physical server will repeat again. The VNIC behaves as if it is a physical NIC. So the VNIC places this packet once again in a ring buffer that exists within the virtual machine. The same process will duplicate, repeat again. VNIC will put that packet in a RxQ buffer, in a ring buffer inside the virtual machine. the packet will then get copied into the virtual memory instead of the physical memory, into the virtual memory associated with the VM via DMA. Okay, the VNIC will now send an interrupt to the vCPU instead of the CPU. It's now an interrupt to the virtual CPU. Right? The vCPU will call the VNIC driver instead of the PNIC driver. The VNIC driver will service this IRQ and it will forward that packet to whom? The network stack in the VM. Where is the network stack in the VM? It's part of the guest operating system. The network stack in the VM will process it, put it into another socket interface to make it go towards the VM application. And that is how the traffic reaches a VM. So whatever happens in a physical server in terms of data copying and processing repeats one more time as the data gets processed within a VM. Why do we keep the same processing? Because of simplicity. We are designing our components as if they are running in a physical machine so that we can reuse applications. They don't care whether they are running in a VM or on a physical server. The TCP/IP protocol stack or the guest operating system doesn't care whether it's running on top of a VNIC or running on top of a PNIC. The interface, the working remains exactly the same. But because of that, the entire operation of data transmission duplicates in a virtualized environment. So each packet goes through the same procedure. And this requires the CPU to be interrupted frequently. It adds significant amount of overhead. And that is the reason why we say that the overlay network sees reduced performance or throughput because of this multi-level of data copying that happens. Okay, so this is the performance bottleneck that arises in overlay networks, and that results in reduced network throughput. So eventually, when you will see, there'll be increase in overall latency. This becomes another kind of a, you can think of it like additional network hop in between. Every network hop introduces more latency. So OVS can be seen as another network hop because it's a switch. And every switch introduces more latency. So it adds to the overall end-to-end network latency, but it also causes reduced throughput in bits per second. The overall throughput will go down because of the extra overhead and data copying that's happening. So now we have agreed to live with this kind of a throughput. More or less we've agreed because we know that the virtualized environment has its own benefits. By sharing my underneath physical resources with many different virtual machines, I am optimizing and improving on my overall utilization of the compute resources. Right? So when we talked about SDN and NFV, in the first slide that I talked about NFV, I talked about the benefit of virtualization from a compute virtualization standpoint. It helps me improve my hardware utilization. So that's a clear benefit. It results in lower costs for the tenants who are using this shared physical infrastructure. At the cost of throughput and some overheads, we've accepted because it gives us lower costs and efficiencies. But there are certain functions sitting in the virtual layer, overlay layer, which are not, which we want to, to whom we want to give better performance compared to what they are getting in general. So when we look at a VM, yes, it eventually receives lower throughput BPS. We are okay with that. But when I look at a VNF, like a vRouter, if I take you a few slides back, the AWS VPC, this diagram, this vRouter or this elastic load balancer, they are all virtualized network functions which are sitting on top of a hypervisor layer just like a VM does. But whereas I can accept some reduced throughput for these VMs, for the VNF network functions, performance is of key importance. Right? I need better throughputs and better performance when I look at a V router or a load balancer, right, as compared to when I look at a VM. Okay, so I need certain methods or techniques to be able to reduce this impact to performance, especially on those physical servers which are hosting VNFs. Right? So whichever physical servers are hosting VMs, we saw this is how the overhead comes in, performance limitation comes in. But when VNFs are being hosted on top of a virtualized environment, I need some methods to arrest some of this performance gaps. How do I do that? What are those techniques? That is what we will talk about next. Okay. Yuvraj has a question. What happens with VM setup where guest operating system is not present? See, the guest operating system is always there, Yuvraj. Okay? What you're probably referring to is the hypervisor architecture where the host operating system is not there. The hypervisor directly runs on top of the bare metal hardware. Okay, but even in that case, when the hypervisor runs directly on top of the bare metal, the key network stack functions, which are part of the host operating system, are included as part of the hypervisor. And that is the only way why the hypervisor is able to run on top of bare metal hardware. So essentially, the overhead that we talked of will more or less remain the same. It's just that the hypervisor may be more optimized when it's running on top of a bare metal, and therefore some performance gains can be obtained in a virtualized environment where the hypervisor runs on top of bare metal hardware. Okay? But the network stack will still come into the picture. Okay. Ravi, can RDMA improve performance? Yes. So there are various techniques that exist. Right? RDMA is one of them. We'll talk about a few. Let us go through these techniques. What are the methods that exist using which I can try to improve the performance? And what I'm sharing is not the only methods. Ravi, as you said, RDMA could help improve performance. In the layer where I send the traffic, yes. So when the VNFs are running on top of a physical server, I can use certain techniques, which we are going to just talk about, which kind of bypass this whole virtualization layer in order to help improve performance. Right? And there RDMA and other DMA techniques can also come in. So there are techniques that have been developed to optimize the performance and overcome this virtualization overhead, especially when I'm deploying virtual network functions on physical servers. Okay, but remember that these technologies cannot be generalized. It cannot be used everywhere because eventually, as we will see, they require some support from the physical infrastructure that is underneath. And I'm assuming, Ravi, when you say RDMA can improve performance, that limitations comes in there as well. You require certain special type of physical infrastructure in order to support those techniques. Our whole data center and cloud ideology has been built around use of COTS hardware, common off-the-shelf hardware, which I can purchase in bulk, deploy in a data center, and use it to run any kind of virtualized environment. But as soon as I say that no, for some performance gains, I need some special type of hardware, not this common off the shelf servers machines. It is defeating to some extent the whole idea of economies of scale by moving towards common off the shelf server machine architecture. Right? So we will see that these performance improving techniques, yes, they exist. And yes, we use them for some special purpose servers which host the VNF functions. So that these virtual network functions, vRouters, load balancers, can operate at better throughput as compared to the other VM. But we don't generalize it, because generalizing would mean all the physical servers will need special hardware support in order to improve the performance. Okay, so take it with a pinch of salt that these techniques which exist are not prevalent across the data center. They are limited to only few server machines in order to support some high performance virtual functions, virtual lay functions, especially these VNF functions. Okay, so these techniques include PCI pass-through, single root IO virtualization called SRIOV, OVS. A new variant of OVS is often used, which is called OVS DPDK. It's basically a variant of OVS that is built using Intel's DPDK technology. Okay. So these are some. I'm not exhaustively covering everything, but these are some techniques that help improve VNF performance. So let's get a flavor of what these techniques are and how do they help. So as the name suggests, PCI pass-through. What is PCI? Everybody, again, I'm assuming you have done a course on operating system in college days, and you know that in a computer system, you connect your physical hardware devices together over what we call as a bus. Right? You have a system bus which connects your CPU to the memory, which connects your peripheral devices like your keyboard, your mouse, to the other CPU memory devices inside the computer. This system bus, right, actually uses a technique called PCI, peripheral component interconnect. The term peripheral component interconnect means this is how you connect the peripheral devices. Keyboards, network interface card is a peripheral device. Right? The physical network interface card is a peripheral device. So it connects to the rest of the computer system devices like the CPU, the memory, using a uh, uh, intercommunication technique called PCI, right? Peripheral component interconnect. It exists in all our computing systems. Now, PCI pass-through is a technique which allows a virtual network function, a VNF, which requires higher performance, the ability to directly access a physical PCI device, like a physical NIC card, um, and bypass the entire virtualization infrastructure. Okay, so on your left is your regular virtualized deployment. This is regular deployment, which we just discussed. The physical NIC card talks to the OVS in the kernel space. The OVS then passes the information to the VNIC. The VNIC driver, by the way, this also you will see is a very commonly used driver. It's called VirtIO, Virtual IO. The VNIC driver is open source again implementation called the VirtIO. It's openly available, and this is what we use inside VMs. The VirtIO driver, it's the VNIC driver. So this is the general deployment that we talked about. But when I need higher performance for my VNF, I want to bypass this whole layer. So I use a technique called PCI pass-through, where a VNF running in the user space is directly mapped to a PCI device like a PNIC, physical NIC card. Okay, so in a way we are saying PCI pass-through gives a VNF direct access to that PNIC card and seems to behave as if they are physically connected together. The VNF being physically connected to the PNIC. Right? That's how it appears to the VNF. So PCI pass-through technology is used to directly map one PNIC card to one VNF, making the VNF and the PNIC appear as if they are directly connected. Okay, so because they appear to be directly connected with the one-to-one mapping, the hypervisor is completely bypassed. The VNF directly reads the PNIC interface, memory interface, to read the network traffic. And this is what enables higher throughput, reduced CPU utilization, and reduced latency, because all those memory copies, interrupts are not coming into picture. Okay. The disadvantage of using a PCI pass-through and mapping directly a VNF to a PNIC card is how many such VNFs can you have running in the physical server? It's limited by the number of physical network interface cards you have in that physical server. Okay, so the number of PNICs that you have in your server machine will limit the number of VNFs that you can run in that machine using the PCI pass-through architecture. So it's not very cost optimized or cost efficient way of doing things. And hence I said, we don't want to generalize PCI pass-through as a technique, because I'm limiting the number of VNFs that can run dependent on the number of physical NIC cards I want, or in vice versa. If I say differently, if I have to run more VNFs on this physical server because the compute power supports multiple VNFs, I will need to add more network interface cards in this server, defeating the whole objective of having common off-the-shelf servers. I'll have to have these special purpose servers with multiple NIC cards. Okay. So it's not a very cost optimized approach, but it does improve performance for VNF. I can have some physical servers where I implement PCI pass-through. Another technique that is often used is called single root IO virtualization. So the term IO virtualization means, and single root means there's one device, one root device. Ajit, that's the whole, to your question, that's the whole idea. I have removed virtualization altogether. I mean, the benefits of virtualization you will not observe in PCI pass-through. Okay? The only reason why I'm still calling it virtualized is because they have multiple VNFs that can be run on that physical server. I can have 10 VNFs running on the physical server if I have 10 physical network interface cards on that server. So it's still a virtualized environment. Okay? But it's not the most cost optimized thing to have, because I have to plug in 10 physical network interface cards, increasing my server cost. Okay. So it's still a virtualized environment, but so I still have, I mean, we are not saying that you don't have the hypervisor, you have it, but I've just bypassed it. I've directly mapped the VNF to the physical NIC card using the PCI pass-through technology. Okay. In single root IO virtualization, the term single root denotes one PNIC card. Unlike here, where I had to have multiple PNICs, SRIOV is a slightly more cost optimized approach, because I don't have to increase on the number of physical network interface card. I can use a single physical network interface card, and therefore the term single root. But in the physical network interface card, I introduce virtualization. Okay, so I have a special network interface card which supports virtualization. So this is your regular deployment, and this is with SRIOV. The difference is this network interface card that you have, it's a special network interface card, which is SRIOV enabled network interface card, which means that it implements the virtualization layer within the network interface card itself. So there's one physical port which connects to the external data center network. But this network interface card has a switch-like functionality inside the network interface card itself. It has a Linux bridge, an Ethernet bridge inside. It's called a hardware virtual Ethernet bridge. So this virtual Ethernet bridge is creating a layer of virtualization inside the NIC card itself. Remember when I talked about network virtualization, I said it's possible to do virtualization at any layer of your protocol stack. We took examples of two. We took an example of a layer 2 virtualization when we talked about VLANs. We took an example of a layer 3 virtualization when we talked about VPNs. You remember that class from NFV? Class number 6 or 7 it was. I hadn't talked about others, but this is another. You are doing virtualization very close to layer 1, the physical layer. As soon as the traffic comes in from the physical layer port, I pass it to a virtual Ethernet bridge. I've taken the virtualization layer right inside the NIC card. Now, what this bridge does is it receives traffic from one physical port and sends it out using flow rules over multiple outgoing ports. These outgoing ports are called functions. The PF stands for the physical function. It's the function which connects to your physical NIC driver, PNIC driver. Right? So this is like your PNIC driver, which already exists in your systems. The PF connects to that. But the virtual functions, like in PCI pass-through, can directly connect to the VNF drivers, VF drivers. So it's like PCI pass-through, as you can see, but it doesn't require the PNIC to be mapped to only one VNF. Right? My same PNIC can be mapped to multiple VNF by introducing another layer of virtualization inside the NIC card as well. Yeah, you're right, Gautam. So I'm saying another layer of virtualization that we've introduced in the NIC card. There is a layer of virtualization above the NIC card, definitely, that's there. Right? This is the layer of virtualization and that exists even now. Right? And in fact, if on the same machine I have some VMs also running along with the VNFs, then those VMs will still go via this path only, as we saw, the traditional path. So via the OVS. But for the VNF, I can directly connect them as if I was supporting PCI pass-through over the virtual functions. So I've created an additional virtualization layer inside the network interface card. And that is why this technique is called single root IO virtualization. The input output from the physical system has been virtualized. Okay. Again, you can see that this requires a special purpose NIC card, an SRIOV NIC card. It's not a general NIC card. So something different has to be done in the server architecture. A different kind of a NIC card has to be procured and plugged in if I need to improve the performance of some physical server machines that are going to host VNF functions. The third technique is more promoted by Intel because Intel has a technique called DPDK. Right? I don't remember the full form if somebody else. Oh yeah, here it is. Data Plane Development Kit. This is Intel terminology, Data Plane Development Kit. They basically created a DPDK framework to improve the performance of the virtualization VM sitting in the virtualization layer. And OVS DPDK is actually a variant of the basic OVS, where the OVS functionality is actually replaced with or integrated with Intel's Data Plane Development Kit to create a new variant of OVS called OVS DPDK. So unlike OVS, where the data plane runs in the kernel space, and because it runs in the kernel space, it causes data copying to happen from the kernel space to the user space. The whole idea in Intel's DPDK is to avoid that kernel space to user space memory copy save. So what they do in general DPDK architecture that Intel brought in is a pole architecture. Okay, what did I talk about in the previous architecture? Again, I'm assuming you have some basic idea of operating system. A lot of this is all OS and computer architecture, computer organization architecture, if you've done those courses in your college days. What did we see here? This whole architecture is a interrupt-based architecture. I'm not sure if you remember this from college days. There are many ways in which data handling is done in a computer system. An interrupt-based system is one where once the data is available, the source interrupts the receiver to tell it that the data has been received. Now you should process it. This is called an interrupt-driven architecture. But there can also be a poll mode architecture. In a poll mode architecture, the receiver continues to poll the source to see if there is any data. Even in software, when we design our applications, we can do either. I can keep on polling, or the sender can interrupt me, send me an interrupt when the data is there to be sent. So these are techniques that are used. DPDK does away with the interrupt based architecture and actually uses what is called as a poll mode architecture. So in DPDK architecture, there's a driver called a poll mode driver, or PMD. The poll mode driver continuously polls the network interface card to see if the network interface card has received any network data. And if yes, then directly read it. Okay, to avoid any interrupt based processing. So this is what DPDK does, and the DPDK components run directly in the user space. They don't run in the kernel space. So when this is like a user space application, the PMD is like a user space application which is directly polling the network interface card, checking if there's some network packet, and if yes, it directly reads it into the user space memory, bypassing the kernel space altogether. Okay. So OVS DPDK is an implementation of OVS. It's a virtual switch, but this virtual switch sits in the user space of the Linux protocol, implementing the DPDK poll mode driver, PMD. Okay. So the PMD continues to poll the physical network interface cards. Again, the physical network interface cards normally don't support this kind of behavior. They are interrupt based. They will always use DMA to copy data into the memory and then generate an interrupt. That's the normal behavior of NIC cards. So these are special purpose NIC cards called DPDK NIC cards, which allow poll mode behavior, which can be polled and which allow direct data reading. So these are DPDK NIC cards. The DPDK PMD driver directly keeps on polling the DPDK NIC cards. As soon as the data is received, it directly reads it into user space memory and then gives it to the OVS to pass it to the VNF. So once now in this architecture, the duplication of data copying is once again removed. So you have exactly like in a physical server, there's one layer of processing of the traffic. That's what will happen in this architecture. Okay. Now the shortcoming of this approach, as we will, as general architects or software engineers, we know the reason why we don't use a poll based mode behavior is because polling, what does it do to the CPU? It completely blocks the CPU. If I write a piece of software that does I run a for loop saying for eternity, forever, keep on doing these functions, what will happen? My software will continuously engage the CPU to run that infinite for loop. Right? A poll mode is like that. When I keep on polling, it will completely engage a CPU. So in Intel's DPDK architecture, the whole architecture is based assuming that you have multi-core CPUs. Yes, multi-core CPU is the norm today. We no longer have single-core CPUs. So it's not so much of a big and absurd choice to make. But I'm just stating that it assumes that you have multi-core CPUs and that one core of that CPU is dedicated for the PMD, the poll mode driver. Because the poll mode driver will continue to poll infinitely the NIC card underneath. So one core of the CPU is dedicated to this polling function that is done by the poll mode driver. The other CPU cores can be shared for other functions. Okay? But one core of the CPU is dedicated to the PMD. Okay? And this is one other alternative, that is Intel backed technique to improve your VNF performance. Okay? Now, in all these three techniques, if you look at them, the pros and cons of using it, as I said, you cannot generalize it and say I will use it everywhere, even to the extent that it will help me improve the VM performance. No, we don't do that. Okay? Because it's a trade-off between flexibility and performance. When I use PCI pass-through or SRIOV or OVS DPDK, we gained in performance, but we lost in flexibility. We required special purpose components to enable them, limiting the flexibility. Why do I say limiting the flexibility? See, if a physical server goes down, this happens all the time in cloud environments. Maybe cloud computing, somebody talked about it. The whole concept of VM migration. I have 100 VMs running on a physical server. That physical server has to be brought down because it has a maintenance cycle. What do I do before I bring down that physical server? I migrate all the VMs that are running on this physical server to another physical server. And then I bring down this physical server. This is called VM migration. I'm migrating the VMs to another physical server. Now, I can do this very easily if all the servers in my data center were all of the same type. And that is why I said we need COTS hardware, common off the shelf hardware. They're all of the same type. So I can move VMs from one physical server to wherever there is space on other physical servers. May not all move to the same physical server. Some VMs may go to one physical server, some others will go to another physical server. I can do that very, very flexibly. But if this physical machine is to go down and I have to migrate these VNFs, I have to search for some special purpose physical servers which also support DPDK before I can migrate these VNFs to those machines. I am losing on flexibility. So it's a trade-off between performance and flexibility. When I use a simple OVS like architecture, which is a standard switch but software based, the beauty of using OVS is that it does not require anything special from the underlying hardware. I don't need any special kind of a NIC card. I don't need anything special from the underlying hardware. I don't need a lot of NIC cards. And therefore, VM migration is very easy and flexible to perform. But when I use any of these other performance enhancement techniques, we saw that invariably they require some specialized underlying hardware to be done. So in one case, I needed a SRIOV NIC card. In another case, I needed a DPDK NIC card. In the third case of PCI pass-through, I needed a lot of NIC cards. Right? So I have to find a physical server where a NIC card is free and spared, and I can dedicate it via PCI pass-through to a VNF before I can migrate it. It's all losing flexibility. So I can only do the migration to those server machines where such hardware exists, not in general. Okay. So it's a trade-off between performance and flexibility, and therefore we use it in a restrained manner on only few servers where I need to install some of my or deploy some of my high performance VNFs. Right? So that's what I wanted to discuss in the context of VM networking and VNF networking. Okay. We'll take a break at this time. We are way past the hour boundary. I know that, but I just wanted to come to a logical point, complete this topic. We can take a break now. And after the break, we will cover the topic of container networking. Okay. How do containers network amongst each other? Right? How does one container talk to another container within a VM, within a physical machine, or even across physical machines or physical server machine? Right? How does this container networking work? Okay, so it's 11:50. Let's come back by 11:55 in 5 minutes from now. Yeah, I hope everybody's back after the break. Gautam had a question before went to break. Are we referring here the container of cloud like Docker and Kubernetes? Actually, we'll limit our discussion to only Docker, Gautam. Um, yes, we are referring to that. Um, Docker is a container management framework, as you might have learned in the cloud computing course. Sorry, it's a container runtime engine, whereas Kubernetes is more of a container management framework. Okay, so it's more like a tool that we use to manage a cluster of containers. Okay, so when we talk about container networking, we are largely going to be discussing the networking component that Docker has. Right? When you look at cluster networking in a containerized environment, where Kubernetes comes into picture, Kubernetes has its own networking components, which we generally call cluster networking. That's not something we will cover. We'll largely focus ourselves to the discussion on Docker networking, just to get an idea of how these things work. We'll see actually that it's quite close to what we have learned so far about VM networking and virtual networking in general. The concepts that we've learned, similar ideologies and ideas apply in container networking as well. Actually, they get extended when it comes to cluster networking and all. The ideas are the same. Okay, another question, Hima Bindu, regarding the upcoming semester exam. Wanted to confirm whether the printouts of the lecture PowerPoint slides will be permitted during. They'll be curated handouts that will be created out of these PPTs and uploaded on the LMS. Okay, we will be giving those. So all 16 lectures, the lecture slides will be collated together into a kind of a handout, right? With a background uh, kind of a print that limits any other copying or bringing other material. It will be created by bits, shared to you with on the LMS page. You will have to download that, print it, and bring it. That's my understanding. But again, the exact instructions will come from the academic operations team. I'm just sharing what I understand as the process. Okay, books and handwritten notes. Again, I'm not certain. See, I don't look into so much of academic operations things. And it's not course specific. It's not as if as an instructor I can say that this is what is allowed for my course. It's a general guideline that is given by the academic operations team across courses. This will be shared with you. So I'm not sure what all is allowed or not allowed. It's something that you will get as instructions from the academic operations team. I think another day or two you should get those instructions. Okay. So I am sorry, but I don't think I'm the right person to be answering these questions with certainty. I'm telling with these from the best of my understanding. But see, there are challenges that we faced, and every time there are changes that happen. Sometimes, in the name of handwritten notes, it's possible for students to bring in anything and everything, and that violates the fairness of the exam. So there are certain decisions which are taken and which the academic operation team will come forward and they will share with you. But for sure, I know that some kind of a slide deck collated together in the form of a handout document will be shared with you from our side, and that you can definitely print and bring for open book exams. Okay, so containers again, I'm kind of going to skip what they are because uh, I asked last time and you said yes, you covered it in cloud computing, so I'm good with it. I think I don't need to repeat what they are, except for a couple of things which I would like to highlight because they are relevant when we talk about networking in the context of containers. So yes, we all see containers as a method of packaging where the entire application code is bundled together along with all the dependencies that it has, like some third party libraries or some data, some configuration files. everything that is required to make that application code run, they are all those dependencies are bundled together into a package, and it's called a container. That's what we see a container as, and that is true. But the container is not just a packaging method, it's also an execution model. Okay, just like a VM is an execution environment, a hypervisor provides an isolated execution environment for a virtual machine. A container runtime engine like the Dockers does something similar. It provides an isolated execution environment for a container or a containerized application. So in that sense, a container is more than just a method of packaging application. It's actually a kind of an execution environment that is lighter in weight as compared to a virtual machine, because as we saw, VMs have their own guest operating system. Containers don't. Containers use the host operating system. So in terms of their computational weight on the underlying infrastructure, they are considered lightweight compared to a VM. But they are more heavier if you compare them with a Linux process, right? A single Linux process. So we say that a container is an execution environment, just like a process in a Linux machine. A process is an execution, is something that I can execute on the Linux system. A VM is something that provides an execution environment for a set of processes within an application, but it's heavier because it has its own operating system. A container is somewhere in between. It allows you an execution environment for a set of Linux processes that comprise that application. But it's lighter because it doesn't have its own operating system. It uses the underlying host operating system. It's somewhere in between a Linux process, heavier than that, but lighter than a virtual machine. Now, a key thing in containers, and this dates back, way back to see Linux kernels, new variants of Linux kernels and versions of Linux kernels keep coming up. There are two key functions in the Linux kernel which power this whole containerization environment. One is called C group or control groups. This is a Linux kernel concept. Right? And the second is called namespaces. Now, namespaces may be something more familiar to you because even in programming environments, we do use this kind of an abstraction, the namespace. And we know that the term namespace literally means, even in a programming sense, an isolated environment in which I can use some variable names, some function names, right? Without them conflicting with similar names of variables or functions in a different namespace. Right? So it's kind of a isolated, reusable environment where I can safely use some function names, variable names, and then outside of that namespace, I can reuse the same names for another namespace. There is no conflict between them because they belong to two different namespaces. So in reality, they are characterized as a namespace, NS, colon, the function name or the variable name. So overall, they become unique. Linux has the same concept. There are namespaces in Linux kernels. And the namespace that we are more interested in is called netns. Okay? So netns is actually the network namespace that Linux kernel introduced I'm forgetting what was the kernel version. Yeah, version 3.8. Linux kernel version 3.8, the network namespace concept was introduced in the Linux operating system. But even before that, in Linux kernel version 2.6.24, the concept of C groups was introduced. So C groups is a name. Okay, let me ask before I go through it. Have you covered this control groups and namespaces in cloud computing course? when talking about containers? Okay, great. That saves me a lot of time. Anyway, yeah. When you guys see that I'm repeating something which you've already covered in a course, just let me know. I can skip those things. Right? They're not required to be repeated. Okay, so we know that there is a method in Linux using which I can limit utilization of Linux resources from a CPU perspective, from a memory perspective. Right? There's a method I can use to limit how much resources of a Linux system can be attributed to a particular control group. There is a method that Linux provides using which I can create isolated virtualized execution environment using namespaces. Right? So it's one operating system, the Linux operating system underneath. But above that operating system, I can create virtualized execution environments, right, where one virtualized namespace has limited visibility into the other namespace. So these namespaces are in a way isolated from each other. So it can be seen as a method of virtualization. Right? So network namespaces really allow us to create in every container its own network protocol stack, reusing the same nomenclature. I can every network protocol stack in a container can reuse, let's say, server port 80, which is the port that we use for HTTP traffic. Right? Running an HTTP server will listen to port 80. So if I'm running HTTP server in two containers, and both containers are running on the same physical server machine, I can do that. Both of them can be running port on port 80 inside of a container because they have their own network namespaces. Okay, so that's the benefit of network namespaces, and that's what comes in handy in containerized applications. I have my unique namespace, my own network namespace, which I can reuse across the containers. Now, what is Docker? So Docker is a platform. It's a runtime engine. It's a platform alongside it set of tools that is used to manage the life cycle of a container. We said containers are software entities. Right? So they are spawned on the fly. They can be spawned on the fly just like a Linux process can be. Right? They can execute like a Linux process. They can be shut down as a Linux process can be. So they have a dynamic life cycle. So Docker is that platform which manages the life cycle of your containers. It also provides the underlying networking capabilities that your containers require to communicate across each other. So literally, it's not the containers which require to communicate with each other. It's the applications which are sitting inside your containers, which are networked applications, and they need to communicate across containers, right, to other applications that sit outside of containers. Right? So Docker provides that networking functions to support this kind of application to external application internetworking. Okay. I'll skip these slides also. I'm presuming you've covered this Docker architecture. It's a client server architecture. This was all there to just give you an introduction to what is Docker and what do we mean by a containerized application. But I'm just skipping them because I believe you've already covered it. So I'll jump directly to container networking. How does Docker provide this networking functionality to applications running inside a container so that these applications can talk to external entities? Now, remember, when I talk about it, these external entities to which the containerized applications are talking with, these external entities could be sitting inside a VM. They could be sitting as a standalone application on a physical server. They could be sitting inside another container. Right? As long as they are accessible using a public IP address or even a private IP address, as long as they are within the same VPC, Docker networking will be able to support connectivity to those external entities. Okay, so what are these network components that Docker provides? Docker comes with a complete subsystem that's called the Docker's networking subsystem. That subsystem includes a host of network drivers. Okay, so these drivers are the bridge driver, the host driver, there's the overlay driver, IP VLAN, MAC VLAN driver, and no driver at all, none. Okay, none is a special case where I say my application is actually a standalone application. It's not a networked application. So it doesn't need to communicate with anybody outside the container. So I use the none driver, which means there's no networking need. Okay. So it's rarely the case today because most applications today, none of them are standardized applications, standalone applications. Most of them are networked applications. So none is rarely the case. We'll talk about the other drivers. Right? So, okay, so before I get to those drivers, let's a little bit about the operating modes of when we talk about container networking, there are 4 modes in which containers can talk to each other. As I said, none driver is used when you use this mode, no network mode. No network mode is rarely the case in modern context, but it is still part of the Docker container networking subsystem. It means container has no desire to communicate with anybody in the outside world. So any sort of network connectivity is not required by this container. With no network. That's one operating mode. Right? It's a mode in which your container can operate. The most common and the default operating mode is called the host network operating mode. So in this mode, the container, oh, I'm sorry, not this. The common one is the single host network mode. I'm sorry. The host network is also a special case. In the host network operating mode, this is also a special mode. The container actually shares the network namespace with the host operating system. In other words, I'm saying the container sees everything that the host operating system sees, and the host operating system sees everything that the container sees. It's like they have the same it's not like they have, it's actually they have the same network namespace. They're sharing the same network namespace. Okay, so there's no isolation between the host operating system and this containerized application. Now you would say, why would I need that? Because this is not the general case. But there are certain functions. See, let me give you an example. Okay, yeah, the example is already there in this slide. FRR. It's an open source routing suite of applications which run as containerized applications. Okay? Now, what do they do? They actually control the forwarding tables in your host operating system. Okay, and because of the fact that FRR is a routing suite for the host operating system, it needs access to the forwarding table in the host operating system so that it can configure it. But FRR itself, as a suite of application, can be packaged as an independent container. It can run as a containerized application in your Linux server. It can implement the entire control plane routing functions for your Linux machine and configure the forwarding tables in your host operating system. So because it needs access to the host operating system's routing table, maybe MAC table, so on and so forth, we say that the FRR containerized application needs to be running in a privileged mode so that it can access the host operating system. This privileged mode in which a particular container can access the host operating system's namespace, we call it the host network mode. It's again a special purpose mode. Only some privileged containerized applications will run in this mode, operating mode. The most general operating mode is single host network mode. It is a default network mode that is provided by Docker. So in this mode, containers which are running on the same physical server machine can communicate with one another, and they can also communicate with the outside world. Okay, so it's like saying I have a container which is running two container applications C1 and C2, and both C1 and C2 can talk to each other. Of course, this is allowed, and each of them can also talk to somebody on the internet. So they could be somebody on the internet, then these containerized applications can also talk to the external world. This mode of Docker operating mode is called the single host network mode because they're running on the same physical server, TS1. The multi-host network mode is a mode where containers running across two different physical servers. Physical server 1 and 2, maybe this is C3, they can also communicate with each other. Okay? So these are four different operating modes in which container networking can work. No network mode, nothing required at all. Host network mode, privileged access required. Share the same namespace with the host operating system. Single host and multi-host network mode. Okay. So the most commonly used driver, okay, that is used in the default Docker mode, which is a single host container networking mode, is the bridge driver. It's called Docker 0. So what does Docker 0 do? So as we said, single host is when you have multiple containers on the same machine and they need to communicate with each other and to the external world. So in the bridge network mode, when the Docker service is first instantiated, a Docker 0 device is created, which actually is nothing but a simple Linux bridge. Like your OVS was a Linux bridge, Docker 0 is like a Linux bridge. Okay, so now when you spawn new containers, right, at the previous slides I skipped, I showed that you can spawn a new container by running the docker run command. Okay? And when you run this docker run command without explicitly specifying the network option, I said the default mode is the single host container networking mode. So Dockers will default to this mode. It will spawn the container. It will create a pair of virtual NIC interfaces called the veth interfaces. Assign one of the veth interface to the container and the other veth interface to the Docker bridge, Docker 0 bridge. Now see that because they use different network namespaces, they can both use the same nomenclature for this virtual Ethernet interfaces. Both are using VH0 and VH1 because they have separate namespaces associated with them. So I can keep on spawning more and more containers, and each of them, the same thing will happen. A pair of VH interfaces, which are virtual Ethernet interfaces, will be created, one assigned to the container, the other assigned to the Docker. So in a way, if you look at it, it's no different than what OVS does. Right? The role of OVS is what Docker 0 is playing. Containers are nothing like VMs, and VMs are nothing like the virtual network interfaces that OVS connects to, use to the VMs. Docker 0 in the bridge mode uses a default subnet. This default subnet is 172.17.0.d0/16. In a way, I'm saying this is star.star. 172.17.star.star. Any IP address from 172.17 subnet can be used. Okay? So that's the default subnet that Docker uses in the bridge mode. Docker 0 assigns itself the address 172.17.0.1. That's the IP address of this Docker 0. And each time a container is spun up, it is also given a unique unused IP address. So this is 172.17.0.1. This container got 0.2, this container got 0.3. Okay. Right. Now, because Docker, as I said, it's part of the Linux kernel system, Docker 0 itself runs in the kernel space. The containers like the VMs, they are spawned and they run in the user mode of a Linux kernel. when a container is spawned, not only is this IP address of .2, .3 assigned to it, the routing table in that container also is fed a default route entry saying that if there is any traffic that you want to send outside of the container, the default route or the default next hop is 172.17.0.1. So basically, Docker 0 acts like a bridge or a switch or a router. Okay? No matter how you want to look at it, think of it like a router. It acts as the next hop to every container. Any container has any external traffic to be sent, the next hop is Docker 0. That default entry is created in every container's routing table. Okay. What Docker 0 additionally does is it configures a NAT functionality. See, all these 172.17, these are what? These are private IP addresses. I can use them as long as I have to communicate within the same private subnet. But if I have to go to an external node in the internet, this is showing the internet. This is a machine on the internet. What do I need? I need a public IP address. Okay. So it also configures a NAT, network address translation function, so that any traffic which has to go to the external public internet can go over the data center network, the edge leaf that we said, the border leaf, and then go to the external internet. So a NAT functionality is also configured. Right? And multiple containers can actually share the same single host IP address, public IP address, to communicate with external network entities using the NAT functionality, network address translation functionality. Okay, so this is how bridge mode of Docker's run. So any container, so container 1 wants to send something to 172.17.0.3, Docker 0 will get that traffic, it will route it to the other container. If it's for an external node, then it will pass it through the NAT functionality over the underlay data center network to send it towards the external network. There is another mode called the MAC VLAN mode. This is an alternative to using the bridge mode. Once again, in single host container networking only, which instead of using IP addresses, uses unique MAC addresses for communication. Okay, so the kernel, when the container is spawned, each MAC VLAN interface is assigned a unique MAC address. And the packet forwarding, instead of happening using IP addresses, will instead happen using destination MAC addresses. So it's like creating a L2 network between the containers. When I use the bridge, I was creating a L3 virtual network, overlay network between the containers. I can use a MAC VLAN bridge, MAC VLAN net driver to create a layer 2 network between the containers. Okay. So that's another driver. Okay, Ravi has a question. Sir, in cloud VM running Docker, it will NAT on the VM IP, right? Yes, that's what it will do. Okay, so it will NAT using the VM's IP address. Right? If Docker is running inside a VM, the NAT functionality of the VM is what the Docker will use. Okay, so the Docker always uses the network stack of the of the operating system it is running within. In the case of a VM, it's running within the guest operating system. So it will use the NAT functionality of the guest operating system of the VM. So you're right, Ravi, in that sense. Okay. Now, so the single host, you can all see it's a simple case. They're running inside the same machine. It's like when I use my laptop to run VirtualBox. When I install VirtualBox on my laptop, VirtualBox is a hypervisor. It allows me to run multiple VMs, right? And then I can connect those VMs using the OVS. It's single host networking only, right? Just the OVS. I don't need anything else. But Docker 0 can have maximum 16 containers. No. 2 to the power 16. Yeah, Ajit has it right. So it is 172.17.star.star. You can assign any numbers to 0 and 0. Right? Last 16 bits are free for use. The first 16 bits, 172.17, have been fixed. Yeah, it's a class B IP address, Jyoti said. Okay, but I don't think everybody understands class A, B, C, D. So yeah, I never use that terminology. Okay, so let's look at multi-host container networking, which is more interesting at the simple single case networking scenario. So we are just 4 minutes away from the class. I mean, extended by 5 more minutes. I hope everybody's fine. I just want to complete it. Right? So what is overlay multi-host container networking? As we said, the physical servers are spread across two different server machines, server 1 and server 2. As you can see, these servers are connected via a underlay clause topology. So this is your underlay data center network. This is the leaf. This is the spine. Right? Um, every server has an IP address of its own. Okay? Now, what do I need to do? If I have to enable container networking across servers, what do I have to do? I have to create an overlay network spreading across these two physical servers. The containers have to be made a part of an overlay network that spreads across multiple physical servers. And when we talked about data center networking technology and overlay networks, what did we learn? We learned that the best way to create this kind of an overlay network in a data center environment is by using the VXLAN protocol. So something that we can do with VMs is, and VXLAN doesn't care whether it is talking to VMs or to containers. All it cares is that there has to be a source entity, a destination entity, which sits across two different servers. And I need a VTEP, which can implement that VXLAN tunnel. The protocol is generic enough. So what Docker uses inside, and actually if you read Docker documentation, it doesn't explicitly say this. The documentation is silent about it. It doesn't make it explicit. But the reality is Docker actually implements the VXLAN protocol. So in a way, I'm saying Docker acts as a VTEP. So a while back, we saw that OVS supports VXLAN, which means OVS can act as a network virtualization edge. It can act as a VTEP, doing VXLAN tunneling and encapsulation functionality and all the other control plane of VXLAN that are supported in OVS. Docker supports the same. Okay. So Docker can act as a VTEP to create VXLAN tunnels across the Docker nodes instances sitting across two different server systems, thereby creating an overlay network across physical servers, just like we do with VMs. Nothing different. And this is what enables containers to talk to each other across two physical server machines. The control plane for this overlay network is the same as what we discussed earlier with the VXLAN control plane. Now, what is the difference over here, which is different from single host container networking? The difference is that in multi-host container networking, I need some method to make sure, see, when Docker 0 was spawning these containers in a server, it was able to make sure that these IP addresses were not conflicting or overlapping. They were unique. But when I do that across servers, how do I make sure that this .3 and .3, they're not reused? I don't want this to happen. The IP addresses assigned to containers across servers, which are part of the same overlay networks, they have to be unique. The IP address is the only way for me to identify a container uniquely. I cannot have overlapping IP addresses across servers. So what do I need in addition? I need a method for coordinating the IP address assignments across server machines so that these containers don't get conflicting IP addresses. And therefore, in multi-host container networking, I need another function inside Docker It's actually called Docker Swarm. Some of you may have heard this name, Docker Swarm. Docker Swarm is nothing, but it's part of the Docker's control plane function that handles IP address management across multiple hosts. Okay. So Docker Swarm makes sure that the IP addresses assigned to different containers across server machines, they are unique. There's no reuse of IP addresses. That's important for me to make sure that my overlay network can be created across multiple server machines without any conflict. Okay. So VXLAN is the protocol that I use just like in VM networking, but I need an additional function called Docker Swarm that can handle IP address uniqueness across multiple server machines. So this is what is covered actually on the remaining slides, how the containers belonging to different subnets belong to two different servers, but the same subnet, they can be assigned unique IP addresses, and then the Docker Zero can act as a VTEP, having its own IP address, and you can create a VXLAN tunnel amongst them. In this configuration, the role of the NAT is implemented. So Docker Zero implements the VXLAN tunnel. The role of the NAT is done by another Docker node called the Docker Gateway Bridge. That implements the NAT functionality for any external traffic that goes outside of the data center network. Yeah, I think though that is broadly what I thought I'll give you an overview of. So you have a flavor of how container networking can also work, but you saw that it's very, very similar to any other VM networking, or creating an overlay network between containers is like creating an overlay network between VMs. And the protocols like VXLAN, which are generic enough, are easily reused with container networking as well. Okay, Ravi has a question how ingress control works in containers. I'm not sure what you meant, Ravi, by ingress control. I am sure you don't mean, but do you mean SDN control? So, I mean, ingress control could mean different things. I mean, you could have, yeah, I can unmute you. Let me try that out. Ravi's there. Okay, Ravi, you should be able to speak.
Yeah, thank you, sir. So what I mean is when we are deploying the container environment, especially like Kubernetes and all, in a cluster environment,
Yeah.
there is a ingress controller is also deployed. So ingress
Hmm.
controller is like it's a kind of like a gateway,
Hmm. Hmm.
right?
Hmm.
So
Hmm.
my doubt was is so just like a bridge is
Correct.
deployed, right? Bridge mode.
Correct. Correct.
Similarly, ingress controller is also deployed. So, but ingress controller is something it control the
Yeah.
or
So you're
manage
talking.
and out
So
for
you're
the end.
talking more about ACLs, the access control list.
Ah, yes, it's a kind of gateway. Yes, application
Yes.
gateway sort.
Yes. So my understanding is that you use the generic Linux concept of configuring ACLs, access control lists, in order to control what traffic, ingress traffic is allowed and what not. So it's like creating those firewall kind of rules in the access control list, just like you do in a Linux host operating system.
Okay, let me give you one example, sir.
Huh.
Like in real time scenario where we are
Mhm.
deploying, like in Azure, we are deploying AKS cluster. Okay,
Yes.
and as a full-fledged networking, we keep the application gateway in front of the cluster, and then
Mhm.
cluster when we are doing deploying the AKS cluster, it is itself also deploying its own ingress controller. So if
Mhm.
ingress controller can be itself it's on internal default ingress controller, or we can use any external ingress controller like application gateway or any other gateway or
Hmm,
something,
hmm, hmm, hmm,
right?
hmm,
My
hmm.
confusion here is, let in many scenario we have ex- external controller like application
Yes,
gateway with firewall, as well as
yes,
we also have internal egress controller. Now in that
yes.
case, when we are defining CNI for the just like another default and network IP ranges, right, for the entire environment. So now
Hmm.
containers are picking the IPs from that CNI driver,
Yes,
and then
yes.
the internal controller is doing a netting. Then
Yes.
again, and because the containers are deployed as a part of VMs inside that, they will have
Hmm.
a VM. Now that netting will be going to the uh, VM IPs. Now from
Yes,
VM
correct.
IP it goes to that external controller. So there are
Hmm.
two level of netting happening, right? One
That is
is
right. Yes,
container to the internal ingress controller, and then from
yes,
ingress controller to the VM IP.
yes, correct, correct, correct.
Okay.
And in fact, you will have the ingress control working at those two levels itself, right? Because the NATing functionality is coming in between. Right?
Okay.
So wherever you have this container running inside the VM, it's another level of abstraction or virtualization that you've created. And as you rightly said, the NATing will use the VM IP address in this case. Okay. So the ingress control will also have to be done on different IP addresses. In one case on the VM IP address, and in the other case in the on the controller IP address. So two levels of ingress control will have to be built in this scenario. If that is what your
Okay.
question was.
Yes, yes, yes. I just wanted to understand the how this netting again and two level of netting is happening. Then
Yes.
communication when we are actually need to control the traffic for the
Yes.
container,
Correct.
then
Correct.
how it is
So
going to work.
yes. So because you've created multi levels of abstraction now, it's like having two layers of virtualization. The physical server running the VM itself hosting multiple containers. So it's like two levels of virtualization that have been built. I, in my slides, used a simple case. I just introduced containers directly running on physical servers. But you're right, I can run these containers inside VMs. That makes it two levels of virtualization, and every layer will have its own network protocol stack and what NATing implemented. So at every layer, you will have to have separate ingress control configured. Right? So yes, it can be more complicated than what I talked in my slides, but I just wanted to give the simpler picture for the broader audience. And yeah, but you're right, Ravi, in what you said. It has to be at multiple layers, the ingress control. Okay, Gotham has a question. Let us just hear that as well. Yeah, Gotham, you should be able to speak now.
Yeah, sir, my question is around the coming examination. So, the handouts that will be uploaded are they will be little bit minimized, or there will be A to Z comprehensive what we
No, no,
have.
A to Z complete. No, A to Z complete. Every slide
Okay.
that I have covered in this class, everything will be put and packaged into a handout and with a watermark, which demonstrates the authenticity of the material being produced by us. And that is what will be shared with you.
Okay.
Okay, so there's some instruction which who's posted this? Arup has. Okay. Okay, so
And
you've already
syllabus will be
received.
full, right? I mean, we have to prepare
Syllabus
full.
is full, so it's a comprehensive exam, so it's full syllabus, but it's quite obvious that the focus will remain more on post midsem. The reason being, we've already covered pre midsem as part of midsem exam.
Yeah.
Uh, but so therefore, more focus. Almost like at least from my course, I can say 70 to 80% of the content or questions will be post midsem, but
Mm-hmm.
20 to 30% can be pre-midsem because it's a comprehensive exam. And the other matter of fact is that everything that we covered post-midsem was based on the concepts we learned pre-midsem. Right?
Yeah.
So,
Yeah.
so in a way, everything will get used, and yeah, it's that way a comprehensive. Right? And yeah, Yeah, I mean, that brings me to one topic. I am not sure right now at this time. I'm in advanced in saying that I may have to miss the last class of our course, the 16th class, because of some personal engagement that is coming up. If that happens, I will inform in advance. And in fact, I will share the slides as well as the video recording for the last class well in advance, even before the weekend comes in, so that you can go through it early enough. And if there are questions, you can post them on Teams and I can answer them. I'll let you know if that happens. But the entire content, right from content session 1 to 16, will come. If I cannot hold contact session 16 for some reasons, before that date, I will share the recorded video and the slide so you can go through it and ask me any questions on Teams. Just some advanced knowledge. I'm not sure yet, but I'll let you know. Okay, so thank you everyone for joining. Next class, we will talk about network security, the topic of security. The last class is about observability. So these are the twin topics that remain, which we will cover in the next two classes. Thank you very much, folks, and see you next Sunday. Bye-bye.